In this video, I'm going to work through a fairly extended example of reverse mode automatic differentiation. So this is the algorithm that's at the core of machine learning libraries like TensorFlow and PyTorch. It's the algorithm for calculating the partial derivative of all of our tunable parameters with respect to our final loss function. So the example that we're going to look at will be this function. And I've picked this because it's kind of a cartoon version of the sort of loss function that we might see when we're training a neural network. So we can think of this as x is the input, y is our target value, w is our trainable parameter. So the goal of this thing is to minimize this squared loss term by finding the right w value. And then we have this w squared term here. This is a sort of cartoon version of L2 regularization. So this is really too simple to be practical as a machine learning loss function, but it has a lot of the elements of what we would see if we were training a neural network. So what I want to do first is kind of take the traditional approach, analytically derive a learning rule for this thing by hand, and then we'll do it again using reverse mode automatic differentiation to kind of compare and contrast the two. So what would the first step here be? What I'm going to need to do is take the partial derivative of this loss function with respect to w if I want to build a gradient descent learning rule. So let's do that. So we know that the derivative of the sum is the sum of the derivatives. So we have wx minus y squared with respect to w plus w squared with respect to w. And then we can apply the chain rule here. So we get 2wx minus y times the derivative of the inside, wx minus y with respect to w plus, and here that's going to be just 2w using the power rule. So all that's left here is to calculate this partial derivative, and remember y is going to be treated like a constant here, and so is x, so this is going to work out to x. So what we'll end up with in the end is 2x wx minus y plus 2w. So this now can be used to derive a learning rule for adjusting w when we see a particular x and y value, and that would look something like this. W becomes the old value of w minus some learning rate, so maybe we pick 0.01 times what we just derived there, this partial derivative. So then we could program this up and we could present some examples of x and y, and for each example we could make a little adjustment to w until we're satisfied with that we're not making any improvements, and then we could call our system properly trained. Let's plug in some numbers here just so we have some concrete numbers that we can use when we're comparing to the algorithmic approach. So let's just say 1, 2, and 3. So L1, 2, 3, that's going to be equal to 1 times 2 minus 3 squared plus 1 squared, and that's going to be equal to, that's 2 minus 1, negative 1 squared is 1 plus 1, so 2. And then let's also calculate this. So we'll plug in w into our derivative formula here. So we get 2x is 2, so 2 times 2, 1 times 2 minus 3, plus 2 times 1, and this works out to, so this is negative 1 times 4, so negative 4 plus 2, so negative 2. And we might as well keep going and make sure that this learning rule actually seems to be working. So how would I then apply this learning rule? Well, if our old weight was 1, our new weight is going to be 1 minus 0.01 times -2. So that's going to be 1.02. Let me grab a calculator off screen and see what I get for my updated loss function. So L 1.02 to 3 then gives me 1.962, 1.962. Oh, and that's beautiful. That's what we're hoping to see, right? We had our loss value here was 2. We made an adjustment based on our learning rule, and that loss function went down a little bit. So if 2, 3 were the only data point we were working with, we could continue making those adjustments until we stopped seeing any improvement, and we would call the system trained. Of course, this is a really dumb, trivial example. We could easily find that minimum analytically, but of course that's not the point. All right, so that's kind of the old-fashioned way of doing things. The goal now is to think about how we could automate this algorithmically in a way that will work for any formula and any set of trainable parameters without requiring us to go through and manually do the math to figure out what the right learning rule is. So let me make myself some space. Let's rewrite our loss function here so we can refer to it. And then let's build a graph where the input nodes in the graph represent the variables, and we have nodes in the graph representing all of the operations, all of the arithmetic operations that are performed in this formula. So let's just see that example. We will have a node for W and a node for X and a node for Y. And then we need to create nodes representing the arithmetic operations, and we'll sort of work outward. So the first one we'll do is Wx, and I'm going to arbitrarily name these things. So I'll call this one L0 equals Wx. And let's make, what else am I going to need? Yeah, let's give it a nice boundary. Okay, we've got Wx. We need Wx minus y. So let's put down here L1 equals L0 minus y. Let's put our edges in. So this is going to be a directed graph, a directed acyclic graph. Okay, now we need to square the result here. So we'll call that L2 equals L1 squared. Put this edge in here. What's left? We need to square W. So we'll put that over here. L3 equals W squared. And finally, we need to add L2 and L3 to get the final result. So we'll put that over here. We'll call that L4 equals 2 plus L3. Okay, so this graph represents this formula. We could view this as a visual aid. We could also view this or implement this as an actual data structure where each of these nodes is represented in a graph structure, and then we could use this thing to perform the calculation, represented by this formula. And how would that work? So let's say we're going to do that same example, 1, 2, 3. If that's the value we want, we're going to assign these numbers to our inputs. So let's use a different color, green. 1, 2, 3. And then we're going to do a forward pass through the graph, and when we reach each node in the graph, we'll have already calculated all of its ancestors, so we'll have the values that we need to calculate the value for that node. So we would implement this by doing a topological sort of the graph, and then working through each node and calculating its value in the order of that topological sort. So here we have w times x. We've already got those values, so it's 1 times 2, so that's 2. This is w squared, so 1 squared is 1. This is L0 minus y, and we've already calculated L0, so I can do that. So that's 2 minus 3, that's -1. That's squared here, so that becomes 1. And then my final value is 1 plus 1, and that's 2. And if I zoom back up to our calculations from before, we see that that's the answer we got when we did it by hand. So not surprising, but reassuring. All right, that's great. It's not really the main thing that we're interested in right now. What we're interested in are the partial derivatives, right? What I want to know ultimately is how do I need to adjust w, and what direction should I adjust w, and how quickly, in order to reduce the value of L4, my final loss function. And reverse mode automatic differentiation is going to do that by now doing a backwards pass through the graph where I calculate the partial derivatives of each of these nodes with respect to that output. So to make that clear, let's just work through the example. We'll pick another color here. How about blue? So we can think of this as each node is sort of pushing the gradients backwards to its parents. So let's start here. This L4, partial derivative of L4 with respect to L3. Okay, and this is going to be particularly easy because since every node represents a single operation, all I need to know is the derivative rules for those operations in order to calculate these derivatives as I go. So in this case, I want to know the partial derivative of L4 with respect to L3. So I can just look here. L2 is treated as a constant. L3 is just the variable. So the answer that I get is 1. Something analogous is going to happen down here. So partial derivative of L4 with respect to L2 is again equal to 1. Okay, now we're going to keep pushing backwards. So we're going to move back from this node to this node. It doesn't really matter. We could have gone here too, right? Remember, now we're working through a reverse topological sort. So let's figure out the partial derivative of L2 with respect to L1. And that's pretty straightforward. That's just 2L1. Okay, so what did we just figure out? We figured out how to adjust this node in order to increase or decrease the value of this node, how changes in the value of this node impact this node. That's not really what we want, right? What I want is, I want to know how the changing the values at this node changes the final loss function that I'm interested in. So this is where we can take advantage of the chain rule. So what I want really is L4, the partial derivative of L4 with respect to L1. Well, that's going to be equal to the partial derivative of L4 with respect to L2 times the partial derivative of L2 with respect to L1, which is what I just figured out. So what that means is I'm going to multiply this partial derivative that I calculated here times this one that I calculated here to give me my overall partial derivative, and in this case that was just a 1, so the answer is still 2L1. And notice we're doing this symbolically here, but if I were using this, right, to learn W or to learn my trainable parameters, there's no need to actually keep track symbolically of what these partial derivatives are. I can just push the numbers back. And I have, right, so here my partial derivative is going to be 2 times L1, and fortuitously, as long as I was clever enough to cache that computation going forward, I have exactly the value I need to numerically know what my gradient here is. So in an implementation, I wouldn't care about what these symbolic representations are. I would just be numerically tracking these values as they get pushed backwards. Okay, so let's keep going. Let's look at this guy. So the partial derivative of L1 with respect to L0 is just going to be 1. And so again, if I want L4, which I do, with respect to L0, I just need to multiply through, right? So it's going to be L4 with respect to L1 times L1 with respect to L0, and it's just 1 times what I had here, so I'm still at 2L1. Doing great. So now I've worked my way all the way back to my input variables. I don't actually care what the derivatives are with respect to x and y. Those aren't adjustable values, but I get them, more or less for free here. So let's do it anyway. So partial derivative of L1 with respect to y, that's -1. And partial derivative of L4 with respect to y, well, it's -1 times this, so that's -2L1. How about x? So partial derivative of L0 with respect to x equals w. And my final answer, L4 with respect to x equals w times this guy, 2L, so, or 2L1, so 2L1W. And something interesting and worrying happens at W here. Right, notice W has 2 children, and they're both going to have some opinion about the partial derivative of L4 with respect to W, and they're both going to push those values back. So the question then becomes, what do I do with those 2 answers? How do I combine them? Let me make myself a little more space here. Erase, I'm going to need a bigger eraser. And it turns out the answer is very easy. I just add them up. I don't think it's super obvious why that's the right thing to do, at least not to me, or at least not to me in a way that I can quickly explain right now. But that's the right answer. So what I want to know, so what these guys are going to push back, right? So I'm going to get, okay, the partial derivative of L0 with respect to W, that's x, and the partial derivative of L3 with respect to W, that is 2W. So then the question becomes, what's the partial derivative of L4 with respect to W? And it's going to be the sum here. It's going to be partial derivative of L4 with respect to L3 times partial derivative of L3 with respect to W. So that's what I get sort of coming back along this path. And then I'm going to add partial derivative of L0 with respect to let's do it the other way. L4 with respect to L0 times the partial derivative of L0 with respect to W. And then I can plug those things in. So that's 1 times L3 with respect to W2W plus L4 with respect to W to L1 times L0x, and that all works out to, well, what is L1? L1 is L0, it's Wx minus y, so 2x Wx minus y plus 2w. I just did a bunch of rearranging, and I did that rearranging because I was really hoping that we would come up with this, the same answer we came up with when we did everything analytically, and it turns out that we have. So everything seems to have come up roses for us. So it worked. We got the same answer by sort of working backwards through our graph as we did by doing the math by hand. But I'll repeat, right, this wasn't really the goal. I don't care symbolically what the partial derivative of L4 is or my loss function is with respect to W. What I really want to do is be able to sort of push those numbers backwards to the graph. What would that look like? And this, and this. All right, all I've left are the sort of local rules for the partial derivatives for just one step. So now if we push things backwards numerically, I'm going to have to make my pen quite a bit smaller. Great. Okay, so what's partial derivative of L4 with respect to L2? It's 1. It's still 1 because that was a constant. Great. What's the partial derivative of L4 with respect to L1? Well, I'm multiplying my way back, right? So it's 1 times this local partial derivative, which is 2 times L1, and I have L1, right? I kept track of that as I did my forward pass, so it's times 2 times -1 equals -2. So this side got what I want here. Push backwards here. I need partial L4 L0. Well, it's 1 times this number. It's getting pushed back here, so it's just -2. We won't do x and y. We'll just go back to W. So now I'm just going to add these things up. So this is 2w times, this is the one coming from this way, times 1. So 2 times nw, I have the value there, it's 1, plus x, and x is 2. 2 times the value that would have come back this way, which was -2, times -2, and that's 2 plus -4 is -2, and I think numerically we got the same thing we did when we did it before. So it worked. So the backwards pass is exactly or just as efficient as the forwards pass, and that's reverse mode automatic differentiation.